Yeah, so what we will discuss today is basically we'll just go through once again with the switch level RC delay models that I discussed in the my previous class. Okay, that's important even for the next unit to cover. Okay, where we'll try to calculate RC delays for using different models. Okay, so that's one thing, and then we'll go with the actual flow of VLSI design. Okay, so what we call it as a VLSI design flow, and then we'll take up one example with respect to the one more RC delay calculation model. Okay, so which we call it as Elsmore delay model that we will take up. Okay, so just going back to the switch level RC delays that we were discussing in the last class. Okay, so we are just uh, taken two things. Okay, so this was what we had switch level RC delay models. So we had considered two MOS transistor. One was with respect to the NMOS. Okay, so wherein we had this NMOS transistor with the three terminals: the gate, uh, the drain, and the source. Similarly, we had taken the PMOS again with three terminals: the gate, the source, the drain. Make sure that why I'm pointing my source up and why I'm pointing source towards NMOS. You have already know that. Okay. So now, since we apply the source, that means the voltage source to the source of this NMOS terminal, and that source is basically grounded. So we try to expect the three capacitance or four capacitance from each terminal with respect to the applied voltage source. Okay, so one capacitance from the gate, another capacitance with respect to the drain, and one more with respect to the source. And all these, and then we have one more which is the body, right? So since the body of the NMOS is having the same potential with respect to source, so we are trying to make sure that the body and the source will take either of one, and predominantly will take the source as one of the terminal with respect to the capacitance. So all this, the source terminal, the drain terminal, and the gate terminal. So the gate, the drain, and the source terminal, what all we are taking, all is with respect to the capacitance exists with respect to the voltage source that we apply with respect to this NMOS, and all the sources with respect to the ground. So that's why we expect three. And body, I have told, since the body and the source are shorted, we are considering only source potential as source capacitance as existing. This is one. And coming back to this PMOS transistor, since the source of PMOS is connected to the VDD of the voltage source, okay, so this is what I mean by the VDD, and there exists again the capacitance from all these three terminals, one with respect to the gate, the source, and the drain, with respect to the voltage source with that to VDD. Okay, so that's why we have one capacitance with respect to VDD. Then we have the gate capacitance with respect to VDD. Then we have the drain capacitance with respect to VDD. And why I'm ensuring that the NMOS capacitance is directed towards down, and the PMOS capacitance with respect to all the three terminals is with respect to source, is all because of the voltage that we apply. And here also the body is connected to this. That's why we are not considering the body terminal. So predominantly we have something like this. Okay. So the gate, the drain, the source, we have one capacitance with respect to the thing, and source is connected to the voltage source, that to the ground. Then we expect one more here, and then we expect one more over here. So this being the three capacitance with respect to three terminals. Similarly, for this is PMOS, the gate, the source, the drain. Since the source is connected to VDD, so we will have all the capacitance with respect to the VDD. Okay, so this is what we are having. Hope you are getting the better view now with respect to the diagram I am writing and all. Hope this is fine. Yes. Oh, yeah. Okay. So this is what we are doing now. Okay. Now, so these were the things. The moment uh, when I take up the NMOS along with the PMOS now, when they are independent, they are okay. But when I'm taking the NMOS and PMOS as a in a circuit, so the moment I take my NMOS, okay, and the PMOS with respect to capacitance of three terminals will be existing. But we have seen one important aspect, that is the mobility. Yes, mobility of electrons and the mobility of holes. So we know that the mobility of electron is approximately twice the mobility of holes. Okay, so that's why we expect the current to be more. In other words, what I can say is, if I want to draw the equivalent resistance of this NMOS, okay, because whenever the NMOS is on or any device is on, it offers its minimum resistance. Okay, so I can consider this is my resistance R. Okay, so this is my resistance R for NMOS. Okay, and what will be the resistance for PMOS now? Based, yeah, what will be the resistance of PMOS considering this expression, that is the mobility of electron is twice that of the mobility of holes. It's all about electrons here. It's all about the holes here, right? Yeah. Fast. In other words, can I say the mobility of, yeah, mobility of holes is half that of the mobility of electrons. So if the NMOS is offering me the resistance R, and what I expect the resistance of PMOS to be. Yes. Yes, Prajwal. Fast. Yeah. Come on. Can I say that if the NMOS, the drain current is something with respect to 5 milliamperes, something. Okay. What you expect the drain current of, sorry, what you expect the drain current of PMOS now for this mobility equation? Yeah. Fast. Fast. Yes. Anyone? Anyone from the group? It's 2.5 A ampere. Okay, it's 2.5 amperes. Okay, okay. Then if that is the case, then what is the resistance that the PMOS will be offering now? If NMOS offers my the R, yeah, so it has to be a 2R now. Is it okay? It has to be a 2R now. Yes. Is this clear? Because of this, okay. Suppose if I use a PMOS and an NMOS in my inverter circuit, okay, in my inverter circuit, so this is my V out, this is my CL. If I use my PMOS and NMOS in this, when PMOS is conducting, provided when V in is 0, okay, my NMOS will be off. So capacitor will charge to peak value, okay, and since the resistance it is offering is 2R, it will take tau is equal to twice R CL, right? Now, the moment when Vin is equal to 1, PMOS is off, my NMOS is on. Okay, now the NMOS will be offering what resistance? It is R. Now the discharging, this is the rise time, the fall time or the discharging time becomes simply R CL. Okay, so that's what we say. There is a asymmetric in charging and discharging. Okay, and hope this is fine. Why we are considering 2R? I think someone had asked the question in the previous session, why 2R and R for NMOS. Is that clear now? Yes. Is this clear? Yeah. Okay. So now, once it is done, okay. So once this is done now, again. So now what we do is we have this CMOS inverter now. Okay. So we are trying to construct a CMOS inverter. Okay, so we have a PMOS on the top and NMOS at the bottom. You can just assume this is a recap of the previous session. Okay, but since it is very crucial, I'm just going with this once again. Okay. Yeah, so this is what we have now. So this is my gate, the source, the drain, the source, the gate. Okay, this is what we have. And now, and also previously, we had one more discussion before. I'm just analyzing. We'll have one more discussion. What was that discussion was? If I have my NMOS, okay, something like this. This is gate, drain, and source. And if I have K as the scaling factor of this particular NMOS. Similarly, if I have a PMOS, okay, with again the gate, the source, and the drain, again with the factor of K, scaling factor, okay. And we had seen two aspects of this, okay. If the length increases, okay, the resistance increases. We had seen the two relation, okay. If length increases, my R increases, okay. That is, R is directly proportional to L, that's what we had seen. And the other one also we had seen, if my width increases, okay, my R decreases. So in other words, we had seen R was inversely proportional to the width. Okay, so this is what we have. Okay. So this is one of the equations that we are interested in. And then with respect to the capacitance, the gate capacitance, we know that it is proportional to the area, and area we are taking in terms of width into L. And again, in this particular expression, I can say that the capacitance is directly proportional to the width. Okay, so this is what we have. And now, since the technology is constant, so I can't take, since technology, once I choose a device of one technology, so it becomes a constant now. So this can't be changed. Okay, since the technology we mean by the L, we can't have a scaling factor with respect to the L now. Okay, so the moment I take a device of this technology, the L remains same, and whatever the scaling I do, that is the K factor. This is all depends on, or it is all with respect to my width now. So in other words, K is nothing but what the width I am considering. Okay, so if K is the scaling factor for this NMOS as well as for this PMOS, okay, so the equivalent of this particular NMOS I'll write in terms of both R and capacitance. Okay, and we know that from the previous discussion, the capacitance exists with respect to the gate. Okay, sorry, I just take out this. I'll just write somewhere over here. Okay, this is my gate. A capacitance exists. Then I have one resistance should be there for NMOS, and for NMOS it is R. Okay, and we have source, and then we have what you call it as the source. Okay, and similarly we have one capacitance with respect to this. Okay, so the equivalent model of this NMOS is R and with 3 capacitance, and since the scaling factor is K, so the capacitance is multiplied by factor of K, whereas resistance is divided by factor of K, because my resistance is inversely proportional to the width, which is nothing but what the scaling now, whereas my capacitance is directly proportional to the width, which is nothing but what the scaling factor. So always the capacitance is multiplied with respect to the scaling factor K, whereas resistance is always kind of inversely proportional, so it is always scaling factor of resistance will be in terms of 1 ohm. Okay, so this is equivalent. And similarly for this PMOS now, okay, so we have gate. Okay, so then again we have source at the bottom. Above we have, okay, so I think what we do is, this is my source I take, this is my drain I will take. Just a minute. Source, I think, yeah, this was correct, not an issue. This was source only. Source, this is not an issue. Okay, that's it. And now when I'm taking up my PMOS now, okay, so the source is up. So this is with respect to my source, and then we have one resistance, and that resistance is something like 2R. Okay, so this is what I am having now, and this is what we have with respect to this. So this is my drain, the source, and all. And again, since the scaling factor is again the K here in terms of PMOS, so the capacitance is directly proportional. It is K times C everywhere wherever we have the capacitance. And since the resistance of this PMOS is replaced by 2R, and now the scaling factor is K, it is 2R by K. So this is what we try to have for NMOS and PMOS. Okay. So for an NMOS equivalent we have this, and for a PMOS equivalent we have something like this. Okay. Hope this is fine till this point. Hope this is fine. Yeah. Fast. Anyone can respond. Yes, so this is what we have. Now coming back to this CMOS inverter. Okay. Now what I do is I have this two, okay, and this one. Why we are making this as 2 and 1, we will try to see. And if this is my V out, and now this output is driving one more inverter. Okay. And the scaling factor of the next inverter, which is getting driven by the first stage, this is stage 1, and this is my stage 2. Okay. Now we have to ensure what is that RC. Okay, the output of 1, okay, is equivalent to input of 2. That is what we want now. Okay, so whatever, so the charging and discharging of this capacitance, okay, the load capacitance, okay, so this is acting as an input for this, whereas the same capacitance is acting as output for this. So we are interested basically in what is the RC delay in between this now. Okay, this is very crucial now. That is the drain of the first and the gate of the second, and this is what we are trying to see now. Okay, so this is what we are having. Okay, so again continuing with this now. So I'm just going with this. So this is scaled by factor of 1. This is this is, and from now onwards you can see that how I connect my VDD, and this is my VDD, and the ground is with respect to this notation. This is my VIN. This is output, and output is now driving one more stage of inverter, right? Again, this is 2 and this is my 1. We have gate, the source, the drain, the source, the gate. Similarly here, the gate, the source, the drain, the source, and the gate we have. Okay, so this is what we try to have now. Now, as I said, we are interested in the drain of first stage of inverter and the gate of second stage inverter. So we are interested in all with respect to the RC existence in terms of the gate, this drain to gate now. That's it. Okay. So now this, whatever the two-stage inverter we have, so this I can have an equivalent circuit. Okay. So if I go with this, with respect to my first stage NMOS, I have R, okay. Since this is my, sorry, the PMOS, the top one, okay, I'm drawing the equivalent circuit for this PMOS. Typically, it is 2R. The resistance of PMOS is 2R. Now, what is the scaling factor given in that particular PMOS? It is 2. So that's why the 2R is divided by 2 now. Okay, this is what we have. Okay, this is 1. And this is my drain I am thing, and this is my source. Okay, 2R by 2. And then I have source with respect to VDD, and the capacitance is C. It is scaled by a factor of 2 because again the scaling factor of 2 is there for PMOS. Similarly for drain, it is 2. Okay, so 2R by 2 eventually gives me R. Okay, so that's why we have R here. Similarly, if I want to go with respect to my NMOS, I have R. Okay, the resistance of, or the NMOS offers me the resistance of R, and what is the scaling factor for NMOS? It is 1. R by 1, which is nothing but what? R only. So that's why it is still R now. Okay, then we have this is my ground. So we have one capacitance with respect to the source now, that is again 2C, and one with respect to this drain, which is again 2C. But again, it is with respect to the ground. The NMOS capacitance are with respect to ground, and the PMOS capacitance are with respect to my VDD. And I'm not considering the gate here because that is not of interest. Anyway, we'll see what are the things. This is what. So now we are interested only with the drain. Okay, so we are interested in the drain capacitance at the first stage and the gate capacitance at the second stage. Okay, so gate of PMOS, that is the top PMOS, I'm interested in the second stage. So gate is connected to VDD again, and the scaling factor is again 2C, and the capacitance with respect to the NMOS, which is sitting at the bottom, that to the gate capacitance with respect to ground is again 2C. Sorry, it is C because the scaling factor is 1 for NMOS. Okay, so you can just see this is what we have. And now you can see that the NMOS, it is short circuit, whereas PMOS is open circuit, right? Because depending upon my input VIN, if VIN is 1 means my NMOS will be on. If VIN is 0 means my PMOS will be on. Okay, that means the drain of either PMOS or NMOS is connected to the resistance. If NMOS is on, my drain is connected to the resistance R of NMOS, and if PMOS is connected, my drain is connected to the resistance R of NMOS. And that's why now you can see that why the scaling factor 2 for my PMOS and the Y scaling factor of 1 for NMOS. Can anyone tell me why we have chosen 2 and 1 as a scaling factor in this particular example? at both the first stage and the second stage. For what reason? For what reason? Yeah,
For making resistance equal, sir.
for making resistance equals. In other words, now I can say that resistance of this and resistance of this are same, means what? The rise time is equivalent to the fall time. Okay, the on to off transition and the off to on, that is zero to high transition and high to low transition, are now symmetric. Okay, so that's why we are ensuring that it is 2 and 1. Okay, so this is what is really happening for us. Okay, so and depending upon my input, so either of NMOS and PMOS will be off. So in any of the input condition, whether 0 or 1, okay, between drain and gate of this, I'll be having one resistance that will be existing. Either it will be of PMOS or NMOS. Okay, so that's why I have one R. Okay, this R may be of NMOS or PMOS depending upon my input. So whenever either of this NMOS or PMOS is on, okay, only R is the capacitance that comes into picture. Okay. Now, what is the equivalent capacitance I am now? Okay. So now the equivalent capacitance, this is my drain, okay, what I'm taking, and considering NMOS is on means this is at ground potential. Then I have 2C with respect to one drain, and sorry, I think this is again the C for me. This is not 2C, NMOS, this is again C. Sorry if I'm wrong. Okay, this is again C. This is again C for me. Okay, this is again only a C for me. It's not. Is that clear? The scaling factor is 1 for NMOS, so that's why C into 1 or 1 into C, it is nothing but what? C. So I have C here, and the same drain is connected to the gate. The input gate terminal of PMOS as a capacitance with respect to VDD. Similarly, the gate of NMOS or the second stage is having a capacitance of C. Okay, so this is what. So I'm just ensuring that I'm covering only these things now. This along with this. Okay, that is what my equivalent thing that I am having. Okay, this is what. Now, if this is the case, in order to find the equivalent RC model here, okay, so we have to ensure that all the sources is grounded. Okay, in other words, the bottom capacitance are parallel, so they become 2C, and the top capacitance again they are parallel, they become 4C. In other words, I have one R here, then I'm ending up with 4C. 2 in parallel means they are added capacitance. Again, that the bottom two are added, so I'm having, this is 2C. Okay, this is what. So the equivalent RC for this particular switch level DC model is, one is R, and this again, in order to find the equivalent capacitance, make sure that all the sources are grounded or given to zero potential. That means this also will be connected to my VDD kind of. It's some kind of superposition theorem that we apply. Okay, you can see that now this C and this C are in parallel. Okay, because both are referenced with respect to ground. Okay, so this I can write it as something like this R. Okay, this is 4C, this is 2C. Again, they are parallel. I can say that R and 4 plus 2, it is 6C. So what is the delay, which we call it as something like a propagation delay, transition or this is called as something like 6 times RC. This is the switching delay for one inverter driving the other inverter with the scaling factor of PMOS2 and with the scaling factor of NMOS1. Okay, so this is where we had stopped in the last class, and how to find out the RC for a switch level. Okay, so the inverter is basically a switch for me, so that's why we are just ensuring that switch level RC is something like 6 RC if my scaling factor of PMOS is 2 and scaling factor of NMOS is 1. Hope this is fine. Shall we move ahead now? Yeah. Any clarification doubts now? Any clarification doubts regarding this? We can discuss. Otherwise, I think we can move ahead. Yes. So with this and with the last concept that we are going to discuss now, okay, it's what we call it as something called the flows VLSI design flow. Okay. So it is VLSI design flow. Okay. I mean, how exactly we start any particular design and how exactly it ends up in terms of the actual fabrication. So we are just so we are just going with the flow chart now. Okay, we are just going with the flow chart. Okay, now if we are starting with any design, okay, so what is the very first aspect that we should know now? Yes. Suppose if I want to design something, what is the first thing that I need? Or if someone asks you to design something, what is the first thing that they should provide or you should come to know now? Yes? Fast. If I ask you to design a NAND circuit, what is that initial requirements will be now? What is that you should know now? If I ask you to realize a NAND gate circuit, the CMOS NAND gate, will you immediately start writing or you'll get some questions to me now? Yeah, what is the first thing that we want? Anyone? Yes. What is the very first thing that we need when we are actually starting designing any concepts? Yes. And the very first thing is something called, okay, the design specification. We need the specification of the design. Okay, when I said I want a NAND gate, CMOS NAND gate, okay, circuit means you should ask, so what are the specification? How many input? Okay, is it a 2-input NAND gate, 3-input NAND gate? Okay, so what kind of logic that I have to use? Okay, whether it is a CMOS NAND gate that I have to build or an NMOS NAND gate that I have to build. Okay, so that's why the very first thing that is very important in order to come up with any design is its specifications. Okay, so that's what the moment we have a specification given, okay, we'll go for designing it. Okay, so designing may be two aspects. One may be a digital, one may be an analog. Okay, so either I can have a design entry, something in terms of the HDL. Now, can anyone tell me what is an HDL? What is an HDL? Yeah. What is an HDL? Yes, Akhil? Hardware description language. Okay, so we already discussed this hardware description language with an example. Okay, so there are more than one hardware description language. I think we had discussed very long in our previous summer vacation what you had. Okay, so either I can go with an HDL, okay, or I can go with the schematic editor. Can anyone tell me what I mean by the schematic editor? Yes, fast. What is a schematic editor? Yeah, like Cadence, Virtuous, or whatever you add is okay. You add a schematic editor, the layout editor. Yes. So either you can have an HDL in terms of the digital description, okay, or I can have a code, then convert the code into an equivalent circuit, or I can directly go for writing the schematic of that. Okay. Okay, so once this is done, so this is what. Once we have a design specification, then go with the design entry either with the HDL or with the schematic editor. Okay, we should have that. Now I have either HDL or schematic. Now, what may be the next thing now I have to do in this flow? Can anyone? Can anyone fix this particular box now? Yes? Yeah, once we have an HDL and schematic, I have written a code for some 3-input NAND in HDL, or I have built a circuit or a schematic of a 3-input NAND. What is the next thing that I have to do? Fast. You already done. I have to go with either the functional simulation. Okay, so either I have to do some functional simulation, or I have to go with logical verification. Okay, so this is what logical verification. Functional simulation with respect to my HDL, the logical verification of this. Okay, so once I have done this, I need to check whether this functionality is correct or not, whether the whatever the design I have done, the way in which I have written a code or in which I have this schematic correct. So I have to check for the functionality is correct or not. Okay, I have to check. Yes. If the functionality is correct, yes, move ahead. If not, no, what I have to do? If the function is not correct, what I have to do? Where I have to go now? Fast. Yeah, so I have to go back to my design entry. Okay, so this is what is all about now. Okay, so something is wrong in my code or some circuit connection is wrong. Yes, maybe the source is connected in terms of drain and drain is connected in terms of so something like this. Okay, so you have to go back, do the entry, once again check. Only when the functionality check is correct, then we move on to next what is really called in terms of, I think those who attended my classes previously when I was doing my HDL class. Okay, so we go for next planning. Okay, planning, placement, and the routing. Okay, which is called PPR, planning, placement, and routing. Okay, then once this is done, then we actually go for checking is design routed properly or not. Okay, if yes, we'll move ahead. If no, I have two no's here. Okay, no, in the left side of mine, what exactly the left side of the screen says is, if it is only the first iteration I have done. Okay, if it is first iteration, go back and do once again check if any necessary thing, or once again go for checking with the design routed. Okay, so if this is the case, go back, okay, and check. If there are continuous iteration that we have done after going here, okay, after going from this towards left, this and this, if I have gone many iteration and still my design is getting not correctly routed, then what I have to do now? Yes, after several iterations, still the design that is getting routed is not proper. So what I have to do now? Where I have to go? Okay, where I have to go now? Once again, go with respect to the design entry that is at the initial stage. Okay, so if nothing is working here, make sure that once again you go with your design entry. Maybe you can even still check the specifications and all those things. Okay, yes. Once the design routed is proper, yes. No means you know what exactly to do. If not, then once it is done, design is routed in a more proper manner, then we have to do what is called as timing simulation. Okay, timing simulation and timing analysis. Timing analysis. Okay, so this is what you have to do. Timing simulation and timing analysis with respect to the design that we have already done. Okay. Then once we are done with that, then we have to see whether the timing specification. Okay, one of the specification in the design may be the timing also. Okay, so I need that my rise time is this much. I want the design to have a rise time of 5 million second. But if it is not meeting, what is that? Okay, is timing specification met question mark. Okay, suppose again for the first iteration, instead of 5 millisecond, if you are getting 5.2 millisecond, okay, so then I need to do, so is everything is working fine, but only with respect to the timing specification. Okay, no, if it is first iteration and if we are doing this, go back to the planning, placement and routing. Okay, if it is the very first iteration, and if it is for many iterations, still I am not getting my timing specification met. Okay, so after several iterations, okay, go back again to the design entry level. Okay, this is what. Then if timing specification is met, yes, then go for actual fabrication into chip. Actual fabrication into chip. Okay, so before actual going for fabrication, till this point, okay, till this point, we have to do all in terms of the simulation using software. Okay, we have to do all this simulation. This is what the VLSI design flow is all about. Yes. So first we need the specification. Then given the design specification, then we have to go for editing in terms of the hardware description language, or we can go with the schematic editor. Yes. Then once we are done with the code or the circuit schematic, then you have to check for the logical verification or the functionality simulation. If everything is perfect there in terms of functionality, move ahead. If not, go back. And once the functionality is done, we have to now do a planning, placement and routing with all these things. Okay, and all these things we will do in terms of some complex program of the logic device or the FPGAs. Okay, so these are the things that we do with respect to the timing analysis, all these things. Okay, so we do all this. I mean, this is just a simple VLSI design flow. There are again some of the other aspects that are involved in this, but these are the main important flow, okay, that we need to focus when we are with the VLSI design flow. Yes. So this is all about your flow chart for VLSI design flow, and this actually completes the unit 1 and unit 2 of our CMOS VLSI design of this particular subject. Yes. Then with respect to the next unit is very important. As I said, we are trying to check or go through different RC models. Okay, so how to find out an RC component, okay, in an interconnect switch or in a line, or when an output of one is driving an input of others. Okay, all these things. Yeah, so for your internals, you'll have the first 2 units of your syllabus. Okay, so unit 1 and 2 with respect to the introduction, where you have all this combination of the schematic, all about we discussed. Okay, so the MOS transistors, I mean basically the brief thing, and what is the CMOS, and what is the pass transistors we mean by, then what is the transmission gate, what do we mean by tri-states. Yes, then designing a multiplexer using the CMOS, the multiplexer using the transmission gate, multiplexer designing with the pass transistors. Okay, so we have now design a multiplexer with three different logic, maybe with the pass transistor logic, or with the transmission gate, or with maybe with respect to the CMOS. Okay, and then we could develop the latches and flip flops again by using this. Yes. Then we saw what we call it as CMOS fabrication flow, especially the NMOS, and then with the CMOS. Okay. Uh, then the layout design rule with respect to my NMOS and PMOS. I mean, in layout design rule, we discussed about the lambda based rules. Okay. So typically, how exactly a transistor is formed in a layout whenever a silicon crosses the diffusion. A transistor is formed with three terminals being the gate, the substrate source and the drain, and the substrate being the body of the fourth terminal. Yes, that's what we've seen. And then the VLSI design for just now we saw what exactly it was. And moving from that, we went to the MOS transistor theory with the ideal IV characteristics. Okay. Then in the IV characteristics, we saw the different regions of transfer characteristics, and in what region of operation the NMOS and PMOS will be in an inverter transfer characteristics. Then we saw the non-ideal IV characteristics with respect to velocity saturation and mobility degradation, channel length modulation, the body effect, the subthreshold conduction, the junction leakage, the tunneling, the temperature dependency. Yes. And then the DC transfer characteristics, as we said, we saw different aspects. Then we saw the beta ratio, effects of beta ratio, the noise margin, okay, all these things. And finally, the switch level RC delay model, that is tau is equal to 6 RC. Okay, so this is what we have for the test for the from the first and the second unit. Hope this is fine. Yes. Any clarifications or anything that is pending with these two units that we have covered? Yes, no means we can go for the next concept, okay, where we call it as circuit characterization and performance estimation. Okay, so this is an important aspect for me. Okay, so that is circuit characterization circuit characterization and performance estimation. Okay, so this is what we have. Okay. And all this circuit characterization and performance estimation is with respect to what is that static and RC component that exists in this. Okay, so and in this particular circuit characterization and performance estimation, okay, so we try to discuss different RC models. Okay, so different RC delay models, different RC delay models, RC delay models. Okay, this is what we have. And we saw one RC delay model just to calculate for the switch level RC design. And in this particular unit, we'll try to see one more called Elmore delay model. Elmore delay model. Okay. I mean, all these are estimation that they are doing. Okay. So all these are the estimation. Okay. So on the theoretical aspect, in terms of analysis aspect, not actually the experimental way of doing. Okay. They are estimating what will be the propagation time delay, the TPD, the time taken for the information to go from one output to the other. Okay, this is one. And then we have something called the linear delay model. Linear delay model. Okay, so we have the another one which is called the linear delay model. And also we have something called the parasitic delay. I mean, in the delay models we have other. So in this linear delay model, we have one of the thing that is very important in the linear delay model is something called as the logical effort. Logical effort. Okay, and also we'll see something called the parasitic delay. Parasitic delay. Okay, this is what we have. And finally, we see the logical effort and the transistor sizing in the next aspect. Okay, so this is what we try to do, not only in single stage, but we'll try to go with taking more than one stage for this. Okay, so now what we try to do is we'll just take one example with respect to the 3-input AND. Okay, we'll take another 2 minutes. I'll just wind it up. Do you people have the next class 9:30 to 10:30?
Yes, sir.
You have class 9:30 to 10:30. Who is taking?
NSP, sir.
MSV sir.
NSP.
MSP. Praveen Kumar.
Hello, sir. NSP.
Vinay Prasad avara.
Professor, sir.
NSP na. Okay. NSP. Okay. So anyway, so we'll just take up 3-input NAND CMOS. Okay. So NAND logic. We're just going with the CMOS. Okay. This is very important now. So which particular logic we are in now. Okay. So for now, when I say 3 inputs, so I have 3 PMOS at the top, okay, and 3 NMOS at the bottom, and the scaling factor of PMOS is 2, okay. Okay. So this drain, the source, the gate, and gate. And then we have 3 NMOS sitting at the bottom, and you know that for a NAND, they have to be connected in series. Okay, and the scaling factor that they have defined for the NMOS is 3 now. Okay, is this fine? So this is input 1, this is input 2, okay, and then we have input 3, assuming that this is connected to this one. Okay, this is what we have. Yes. Now we know what are the capacitance existing and what are the resistance kind of thing. Now, so if I want to, now if I write something like this, are people in a position to understand now? Is it okay? Is it okay why I'm writing all these things now? Yes, with respect to the one of the PMOS, I have 3 capacitance with respect to the VDD. One is the gate, the source, and the drain. All the capacitance are scaled by a factor of 2. Oh, this is fine. Yes, no. Yes, why I'm writing 2C? Okay, you should be in a position. Similarly, I have again a capacitance existing for this 2C. For this, it is 2C, and for this gate is again a 2C for me. Similarly, 2C, 2C, and 2C. This is what I have. Similarly, for NMOS, if I want to go, so with respect to this drain, I have an NMOS with respect to the ground, because you should know that the source of NMOS is always pulled towards the ground potential. Yes. What is the capacitance that exists now in for this particular drain, source, drain, source, drain, and source? Yeah, what is this capacitance value now? Yes. What is this capacitance value now? Fast. I'm interested in the drain to this drain of NMOS capacitance. How much is this? Fast. Fast. Scaling factor is 3. Yes. Anyone can respond. Otherwise, I'll call your name. What is the capacitance of the drain, this gate, or this source will be now? Fast. Yes. This is 3C. This is 3C, and this is now 3C. Yes. This drain, and similarly, this is again 3C. This is again 3C. This is again 3C. Okay, so these are the things. Since the source and drain of this terminal is short connected, it is common. This is again this source and drain, they are one and the same form. Okay, so this is how we have to go with respect to it. And the resistance of each NMOS is R by 3, R by 3, R by 3. Here it is R, R, R. Okay, you know why exactly it has to be an R. So I stop it here. Okay, in the next class we'll take up the how to find the delay model with respect to an L. I think we'll stop here. And Anubhav,
Yes, sir.
are you people free from 4:30 to 5:30? We'll have an instruction class.